Let's build a 24-volt high-capacity lithium iron phosphate battery pack from individual cells. In this tutorial, we will guide you through the necessary calculations and provide a step-by-step assembly process to complete the battery pack. First, we need to calculate the capacity requirement for the battery pack. Calculate the total capacity you need based on your application's power consumption. For example, if you need to power a 500-watt inverter at full load for 4 hours, you'll need a battery pack with a capacity of at least 2 kilowatts/hour. If you want to calculate the capacity requirement for individual appliances used during the night for a solar system, you can do it as follows. For your convenience, you can use eTools Buddy QR code power calculator for your appliances. Simply input the number of hours you'll use them with battery power. For our system, we plan to build a 5 kilowatts/hour battery pack. Then we need to choose a suitable system voltage based on your load requirements. Higher voltages can reduce current flow, leading to thinner wires and lower energy losses. However, safety is crucial. Higher voltage systems can be more dangerous if not handled properly. Ensure you understand the risks at higher voltages and take proper precautions. For our system, we choose 24 volts as the system voltage since my inverter is 24 volts. After deciding the voltage of the system, which is 24 volts, then we need to determine how many individual LiFePO4 battery cells we'll need to connect in series to reach that target voltage level. For example, a 12-volt pack would require 4 cells wired in series, which will be 12.8 volts, while a 24-volt pack would need 8 cells in series, will be 25.6 volts. Connecting cells in series increases the voltage. For a 24-volt system using 3.2 volts LiFePO4 cells, we need 8 cells in series because 3.2 volts multiply by 8 equal to 25.6 volts. Connecting cells in parallel increases the capacity. If you want to build a 460 ampere-hours 24-volt battery pack, then you need to use cells that connect 2 sets of 230 ampere-hours cells in parallel. Now we are going to finalize our battery pack cell arrangement. For our 24-volt, 230 ampere-hours pack, we will need 8 cells in series and 1 cell in parallel formation. This means that 8 cells are connected in series to achieve 24 volts, and only 1 set since we achieve 5 kilowatt-hour capacity. Before buying LiFePO4 cells, we should consider its spec and price related to specifications. Following table includes the main key features and spec that one should consider when selecting an LiFePO4 cell technically. Depth of discharge refers to the percentage of a battery's total capacity that has been used. For example, if a 100 ampere-hours battery has discharged 80 ampere-hours, it has an 80% DOD. A higher DOD allows you to use more of the battery's capacity, but it can also reduce the battery's lifespan. Cycle life is the number of complete charge and discharge cycles a battery can undergo before its capacity degrades to a certain level, typically 80% of its original capacity. The more cycles a battery can endure, the longer it will last. The cell capacity is the total amount of electrical charge a battery can store, measured in ampere-hours. First, we remove the protective foam from each battery cell. Now let's start first step of building our LiFePO4 battery pack. Next, we connect all the battery cells together using metal bus bars. These bus bars provide a reliable electrical connection between the cells. Now, we start building a wooden trolley for a sturdy and secure framework for the battery pack. Then, before inserting the battery pack into the trolley, we thread the necessary components and apply compression. This ensures the battery pack's optimal performance and safety. After inserting the battery pack into the trolley, we need a couple more things to finalize its assembly. The battery management system is an essential part of any DI battery pack design, as it safeguards the cells by monitoring charge levels, balancing the cells, and preventing issues like overcharging, deep discharging, and overheating, ensuring both safety and optimal performance. Our system operates at 24 volts, and your inverter requires 2500 watts of continuous power. We can calculate the required current. Therefore, you'll need a BMS rated for at least 104 amperes to handle the load safely. It's advisable to choose a BMS with a slightly higher rating, such as 120 amperes or more, to provide a safety margin for peak demands and ensure reliable performance. In addition to the discharge current, you also need to consider the charging current when selecting the BMS. For example, if your solar charge controller is rated at 60 amperes, the BMS must be capable of handling this charging current safely. When selecting a BMS, it's important to check if balancing is included. Passive or active cell balancing ensures that all cells maintain similar voltage levels, which extends battery life and improves performance. If the BMS does not include active balancing, as in the case with your DALI BMS, you will need to purchase a separate active balancer to keep the cells balanced during charge and discharge cycles. Active balancers are more efficient as they redistribute energy between cells rather than wasting it as heat. When connecting wires for a BMS, specifically the black wire and the red wires, follow these basic steps. Connect the black wire to the main negative terminal of your battery pack. This is usually the most negative point of your entire series of cells. Each red wire corresponds to a specific cell or group of cells, starting from the most negative side and moving to the most positive. The first red wire goes to the connection between the first and second cell. The next red wire connects to the positive terminal of the second cell, and so on. Connect all other 6 wires likewise and make sure to follow the BMS wiring diagram. Finally, connect both the charger and the inverter to the battery pack's main positive terminal and the BMS load output terminal. Now that we've covered all the essential design steps for the LiFePO battery pack, it's time to move on to the assembly process. Now, we carefully insert the connected battery pack into the wooden trolley. This trolley provides a sturdy and secure framework for the battery pack. Following the instructions we discussed, this is the final outcome of the LiFePO battery pack after installing the BMS, active balancer, and a 125A fuse to ensure the BMS's safety. Finally, insulate all exposed terminals, add the finishing touches, organize the cables neatly, and test the connections to ensure everything functions properly. Once confirmed, you can connect your battery pack to your system. And with that, our full LiFePO battery pack building tutorial is complete.